Hey, welcome to Integral Calculus Part 7, and this is Kinematics. You know what that is from differential calculus. That's the study of motion, and look at what I've got for you here. It goes back, right back to one of the original presentations on introducing differential calculus, where Newton had a displacement time graph, which was a curve, and remember what we said, v-inst, the instantaneous velocity at that point, was the slope of the tangent to the curve. Okay, so what we said therefore in deriving that was that the velocity was the derivative of displacement with time, and acceleration was the rate of change of velocity, or the derivative of velocity with time, or the second derivative of displacement with time. Okay, so do you remember all that? Because that's fundamental to what we're going to be doing now. Because, of course, integration is anti-differentiation. We're going to come back, and I guess you knew what had happened. What if we had a problem where we were given velocity as a function, and we had to go back to displacement, don't forget, plus c, that would be integration, or we'd have to then go on and get acceleration, and that would be the derivative, v dash t, wouldn't it? So we could have to go either way now. So you can see what's coming up. Let's go and have a look now at some of the problems there. And so here's a summary again of what we've just done. The speed, time graphs, the area under the curve there is the distance travelled. We talked about that before, distance travelled, and in both of these cases. And of course, because these are standard sort of geometric figures, we could find that total distance travelled using geometry. But down here, of course, where we have a curve either above or below the axis for velocity with time, then the area is not a known shape. And so that's where we're going to use integral calculus. Okay, calculus to the rescue there. Okay, we could use it up here as well, but we certainly must use it down here. There isn't another way of finding that area. And so we've got a velocity time function from t1 to t2. So distance travelled between those two times is integral from t1 to t of t1 to t2 of velocity with time. And it could be a negative because what are we saying? The rectangles have negative heights, and therefore that definite integral would have a negative value. So I'd have to put a minus in front there. All of that is basically revision, isn't it? Remember all that stuff. Okay, so let's have a look at a summary of that. So displacement function is the integral of velocity with respect to time. Going backwards, don't forget to use plus c. And then if we wanted the total displacement here, st2 take st1, change displacement there, is the integral from t1 to t2 of velocity with time. Okay, distance travelled if you like. So find the total distance travelled. What are we going to do? We have to check it though, don't we? We have to make sure it doesn't change direction. Draw a sign diagram. Remember we did this before. A sign diagram for velocity. Okay, so it might stop at a couple of points. Might be going along, stop, change, go along here, stop, change direction, and go on. Remember all that stuff, the sign diagram from the differential calculus section. Okay, so then we'd have to integrate the function and find each time the direction change, like this up here, and draw the diagram and find the total distance. So the total distance would be distance up to the first stopping point, and then plus the distance back, and then onwards. Remember that? Do you remember those steps? So that's important. So the total distance travelled therefore would be the sum of each of those little sections. Now, if you didn't want to find these stopping points and where it changed direction, remember integration where we use the absolute value or size of the number or modulus of v. So this avoids considering the change in direction. Okay, so if it's in paper 1 in this course, you could actually use, paper 2, you could actually use the calculator and just put absolute value v of t. You wouldn't have to worry about it changing direction, okay, because you wouldn't have to worry about the negative value there. Alright, so let's have a look at finally summarising all this stuff maybe. Like the velocity during the last step now is the integral of acceleration, because we said to get the acceleration of the body it's the rate of change of velocity, so it looks like that. So if we want to come back to acceleration, then velocity is the integral of acceleration, because acceleration is the derivative of velocity. So we want to have the antiderivative. We're coming backwards now. Alright, so what's the summary? Here it is, forwards and backwards. Keep your wits about you here. Differential calculus on the top line. Get displacement, find its rate of change with respect to time, you've got the velocity. And if velocity is changing with respect to time, it's acceleration, or the second derivative of displacement with time. And coming back, anti-differentiation. It's going to be integrating. Don't forget the plus c. So that's what we're doing, forwards and back, forwards and backwards, and so on. So you want to be flexible with that, because you could be given any of those quantities. Let's have a look at a problem. There isn't much in this presentation now. It's just the same as differential calculus, going both ways though. So here we are. We've got a velocity function right in the middle. Answer find without using a calculator. So this is a paper 1 type question. How far does p travel in the first 4 seconds of motion? Find the displacement of p after 4 seconds. Alright, let's have a look. So there are steps. First of all, you're given the velocity, and so let's draw a sign diagram. Let's find where it stops. It stops at 1 and 2. Okay, I like students to put in sign diagram for v of t. Okay, so in this region between 0 and 1, you sub a value into v, find its sign. Between 1 and 2, and then greater than 2. I'm not going to mention in this course there is a quicker way of actually doing that, using the idea of a quadratic, having sign changes positive, negative, positive, but you can do that if you think about it. Okay, p reverses direction at t is 1 and t is 2 because it stops, and the signs change. Okay, so now what is the displacement? To get the displacement we've got to integrate, and we have a plus c on the end. So let's work out its displacement at all these points. So first of all, at t is 0, what's its displacement? Sub t is 0 into this expression, you get just c. Then find where it is at 1. So sub 1 into the expression, you get c plus 5 on 6. Sub 2, you get c plus 2 thirds. Sub 4, you get c plus 5 on 3. So let's take an arbitrary point there on a displacement line there. So it's c, then it goes to c plus 5, 6 out to there. At t is 1, see it, there it is there. And then at t is 2, it's back at c plus 2 thirds. And then at t is 4, it's right out at c plus 5 thirds. So we've got to actually add up all those little motions. So let's have a look. The first one is c plus 5 on 6, take c. So that's that there. And then c plus 5 on 6, take c plus 2 thirds. The distance in between these two. And then c plus 5 on 3, take c plus 2 thirds. Okay, so you've got to split this motion up in all its pieces. And the unwieldy thing is, don't forget c. They've all got c in them. And we weren't given any information here so we could evaluate that constant of integration. So all the C's go out and we've got in fraction land. Now this is quite difficult for some people here. So 5 6 plus 5 6 is 10 6. Let's to see what we can do here. Take 2/3 is 4 6. Change it all to 6. Okay, and that would give us 6 6 or 1. Then we got 5/3 would be 6 1/3. Take 2/3. So that comes to 5 2/3. A third, take 2/3 is negative third. Take off that from 6 is 5 2/3. Bit messy, isn't it, in paper 1 there? Okay, just check your skills there. Now the displacement's also the total distance travelled is 5 2/3 metres. Bit messy with C floating around. The displacement is the final position minus the original position. Total displacement in the 4 seconds. So it's S of 4, take S of 0. Now notice that this is irrespective of direction. Okay, we don't look at whether going up and back and up and back. We ignore all of that. So it's simply the displacement at the end minus displacement at the beginning. And so it's C plus 5/3. Take the original C, it's 5 1/3 metre. Notice the difference in the answers there. Okay, one is simply working out how much further to the right it is from when it started, if you like. Okay, so displacement is, change in displacement is 5 1/3 metres to the right. Alright, notice that rather than going up and back with your motion diagram and your sign diagram for velocity, you could just put this in the calculator. Just watch the steps now. You go to run mode, you go to options, calc, choose the integral sign, put the limits in, but then to put the function in here, you've got to go to options, number, and choose abs, absolute value. So you can only do it on the calculator in this way, and this is if it's in paper 2. This way you get the same answer. What it's doing is it's allowing you to take the velocity function as a positive function throughout the interval. Don't worry about the fact that it goes under the axis. If you actually plotted this function, if you remember at x's 1 and 2, it'll be under the axis there. So this ignores that. Don't have to worry about that. It doesn't ignore it. It accommodates it with the absolute value, taking it across that interval. Alright, are you ready to do some yourself perhaps? Here's some here. You might have to go back and check. So here we're generally starting in the middle of the process with the velocity function, having to integrate to go back to displacement, differentiate to go on to acceleration. So you've got to keep your wits about you. All of these are velocity. They're in the middle, if you like. If you have to differentiate to go to acceleration, integrate to go back to displacement. Alright, have a go at those 3. I'll show you the rest and then I'll show you the answers. So pause the presentation, have a go. Let's have a go now at the other few down here. Down to number 7. Okay, very important to try the ones with E and cos in them. They are very likely problems in this course. So have a go at those, trying to go through the standard procedure that was up above. Alright, these screen clippings are from Hayes publications. So you might have a look there, and here are the answers. So check the work with fractions, try to do it without the calculator as if it's in paper 1, and just make sure you can work without the fraction, with the fractions there. Okay, let's go on and have a look at some more. Here's another problem of interest to you. Here we go. This time it's given an acceleration. Okay, it's moving to the right at 5 centimeters per second. That's a velocity, and it accelerates with that. Answer the following without using a calculator. So it's paper 1 question. Find the velocity function of the particle and sketch its graph. Okay, The velocity is the derivative of velocity acceleration, so you're going to have to integrate it. Come back to the velocity, integrating that, don't forget the c. But now this time it's a little bit neater. We're told at the beginning the acceleration or the velocity is up here 5 centimeters per second. So c is 5, subbing t is 0 in, you therefore have a constant value of c is 5. Okay, so just checking that. Okay, so now we have to integrate that to get the displacement. But the first thing was to get this function here, and we've just done it. So we can now draw its graph. So neg t squared plus 4t plus 5. You'll find where it cuts the x-axis. Here at 5 and the y-axis at 5, and draw the graph, subbing in the value from 0 to 6. Make sure here you sub in 0 and 6, and to get the vertex here quite accurately, you'll need x equals neg b over 2a for that vertex value there. Okay, neg b over 2a, which is neg 4 over 2 times neg 1, or neg 2, so this is going to happen at 2, and you could sub it into the function to get that y value. Depends on how accurately they want it. Let's have a look at that, sketch its graph. So a sketch is only fairly rough in the IB sense, it's a command term. Draw a diagram is more specific and requires more accuracy. Alright, I just want to check back here, could you find the x-intercepts of this function? Neg t squared plus 4t if it was in paper 1. Doing that, so maybe multiply through by neg 1 and get that. Use the roots of a quadratic, or can you factorize like this? Okay, something like that. Oops, I think, hang on, we'll just go back down here and have a look. I have to have a plus 1 in there, don't I? Neg 5t plus t is neg 4t, so we'd have values of t is 5 and t is neg 1. Of course, we discard that because t is greater than or equal to 0. T is time in this problem. So just remembering that, or would you like to use this formula for the roots of a quadratic? Something like that maybe. Okay, to get that intercept there, and the other one's over here at neg 1, of course. Okay, what about the second part of the problem? The displacement of the particle, so we need to integrate it. We're integrating velocity now, we've got it. Increase each power by 1 divided by the new power. There it is. Don't forget the c. Now, they've been a bit naughty here, haven't they? Because you shouldn't use c when you've used it before in the problem. Should use k. Because no one says this c is the same as this one up here. So in any problem where you want to introduce a constant where you don't mean the same constant, you should allow for that by putting in k, because actually the constant is 0 here, where c up here was 5. Please note that you should put in plus k there. And then we say when t is 0, s displacement is 0, it tells us that further up in the problem, and so the constant is 0. So that's k is 0 in there. Important. So the displacement of the particle in the first 6 seconds is displacement at 6 minus displacement at 0. So that's a change in displacement, and that's 30 centimetres. Subbing those numbers in. Then let's have a look at the total distance travelled now. And if you have a look at the total distance travelled, let's have a look at, first of all, when does it change direction? So you're going to put the velocity equal to 0, and we found that already as 5 seconds. So find the displacement at 5, and what do you find? It was at 0, and t is 0, displacement was 0. At 5 it's 33 1/3. Then it changed direction, so we need to find it at 6. So subbing it in at 6, we get 30. So then the total distance travelled is the initial distance from 0 to 33 1/3, and then it's come back this 3 1/3. Notice that the distance travelled doesn't have a sign, it's a scalar, it's not a vector, displacement's a vector. So here therefore it's 36 2/3. And you could have done it again with technology if it's not in paper 1, because you don't have to worry with technology about this change in direction. The fact that the velocity's gone negative. We can use the absolute value of the velocity expression. So keep all those things in mind. Okay, let's have a look at some problems for you down here. And we just got a few here, 8, 9 and 10. Interesting ones, interesting functions. Okay, so go carefully through the steps. Follow a set procedure, thinking about what you're doing, a sign diagram to see where it changes signs. And then, so that's for paper 1, and then check with technology. I think that's important in case you are able to use it in paper 2. Right, pause presentation, have a go, and let's go and look at the answers now. Okay, so there's some answers for you. I haven't got the work solutions here. You'll have to battle on and see if you can get those numbers yourself. Just go carefully through those set steps. Well, I hope you've enjoyed that. You're building up skills. Watch out for these sorts of kinematics problems where you're asked to go both ways, differentiate and integrate. But if you work carefully, you'll be okay. Remember, you've got a formula book, so you can use that for some of the integrals of common functions. Don't forget the plus C every time. All right. Congratulations on building up the skills, and I think there's just one more presentation in integral calculus where we're going to look at an interesting application, volumes of solids of revolution. So that's quite an interesting one. So I'll catch you then. Cheers for now.